It's our honor today to have Professor Erich Poppitz from University of Toronto. He, he will be telling us the story of the domain walls, anomalies, and deconfinement. And let's welcome Erich. Please take over.
Thank you, Jovan, for inviting me. I hope you can see my cursor. Is it moving? Yeah, thank you. So yes, the topics is domain walls, anomalies, and deconfinement. And the bulk, or rather the end of this talk, will be devoted to this work with actually 2 undergraduate students, which started the summer project as a summer project, but it is related to that topic. And most of my talk, I will probably spend explaining an old work, Pre-Anomaly, with Mohammed Anber and Team Sulejmanpasic from 5 years ago. And we will see how this ties up with these modern developments. On axion domain walls, I probably won't have much time to talk. So I come from the particle physics side of things. Actually, I don't know exactly who is in the audience, but we're reductionist people. And we want to know, given a set of ultraviolet degrees of freedom, usually weakly coupled, so asymptotically free theories, we want to know what these theories do in the infrared. And this is a very difficult problem to address because of strong coupling. And we have few precise handles on this problem, and anomaly matching is one of them. It is a set of numbers that we can compute in the ultraviolet theory, and that set of numbers computed in the infrared theory should be the same. So it limits fantasies we may have about the infrared behavior of theories. And at least I thought that anomaly matching was set in stone. You know, when I learned about it, this happened in the 90s at some point, anomalies of zero-form symmetries, that is to say normal symmetries that act on local fields, they played a major role, for example, in prion models of composite models of elementary particles, or during my time in the study of cyber dualities. It was very important to understand Hooft anomalies. And so it came to me as rather a surprise and a deep revelation that things have not been quite as well understood as they should have been. And it turns out that there are new generalized anomaly matching conditions due to these people. And that has been quite a exciting development for the last 5-6 years. And I don't want to give a definition to this generalized anomaly matching, but roughly speaking, at least the ones that I'll be talking about, there are anomalies of global symmetries which are revealed when you turn on background fields for global symmetries, also background gravity backgrounds, but in a way compatible with their faithful actions. So you have to be very careful. And some of these can be interpreted as gauging higher form symmetries. So this is the kind of revelation of these generalized anomalies. So currently it is a very active area of research across fields. There is condensed matter literature, there is mathematical physics. People try to classify what kind of anomalies can be. They can try to make some general statements. I come from the high energy theory end of things, and the way I like to understand things is by studying examples and dynamical implications in quantum field theory. So this development is impossible to review, and so my references are quite scattered here and there. And if for better list of references, please consult the papers. But I will mention 2 papers which came after our domain wall papers, and I think they're relevant to this talk, as I will mention in the end, in particular a paper by our host. Also, I must say that it's not just impossible to review, I find it impossible to follow everything in real time because some of the language is quite foreign to me. So another thing I want to say, please ask questions, and I'm happy to reveal my ignorance wherever it shows. So I will narrow this talk's subject as a very broad subject. I will narrow it to theories with a broken zero-form global symmetry. So a zero-form global symmetry is some normal discrete symmetry, say a Zn cyclic symmetry, and an unbroken center symmetry. And so this is what I will study, theories with such kind of vacua. And in plain language, those are confining theories with domain walls. So domain walls because there is a broken discrete symmetry, and confining because there is an unbroken center. And the kind of theories that what I will be talking about is relevant to is, for example, Young-Mills or QCD with massive fermions at theta equal pi, adjoint QCD with numbers of our flavors, if they happen to be not CFTs, and for example, QCD-like vector-like theories, coupled to axions, which I won't have time to talk about. So in all these theories, so these are confining theories with domain walls, a very general phenomenon is predicted by these modern anomaly arguments. So here's a cartoon. There is a domain wall, and there are two vacua on the two sides. And in these two vacua, if one puts in probe quarks, some heavy quark anti-quark pairs, the color flux tubes stretch in this sort of string-like configuration. And they give, so we say that this is confinement, and it gives rise to area law for the fundamental Wilson loop in the bulk. But once you take this Wilson loop to the domain wall, then it turns out that this string melts, but there is no energy cost, there is no linear potential anymore between the quark and the anti-quark, and they can propagate along the wall without any cost in energy. So the Wilson loop on the wall obeys perimeter law. So the explanation of this phenomenon on domain walls has been somewhat formal. I give several pictures here, several points here. So the oldest ones are the one on the top and the one on the bottom. So a very long time ago, in the framework of super young Mills, Achari and Vafa proposed that there is a three-dimensional Chern-Simons theory that lives on the domain walls. And this is recently has been connected to these mixed anomalies. And I will review these arguments. And so the argument here is that in three-dimensional Chern-Simons theory, there is no confinement. The Wilson loops obey perimeter law. And if you identify those Wilson loops with the bulk Wilson loops, it's naturally to suggest that there is deconfinement of the walls. A more heuristic physical argument has been given for a long time since the work of Witten on branes and the dynamics of QCD. And it's also, some of it is attributed to Sue John Gray as well. And the picture uses a heuristic monopole Diane picture of confinement. So we have a domain wall. And on the two sides of the domain wall, there are, the confinement is due to the condensation of either monopoles on dions. And those are mutually non-local particles. And so on the wall, nothing condenses. And if nothing condenses, the theory doesn't confine, the flux spreads. So this is a heuristic explanation. It has more recently been also given by these people. And of course, as already Witten noticed at that time, in non-supersymmetric theories, apart from Seiberg-Witten theory, these monopoles are somewhat elusive objects. So the subject of my talk is essentially to address the following question in a simple-minded framework. Is there a framework in quantum field theory where we can understand the domain wall deconfinement in a theoretically controllable way using dynamics? And it would be nice to have a more concrete physical picture. So this is my goal. This is difficult on R4. It entails having a theory of confinement. And apart from Seiberg-Witten theory with a small supersymmetry breaking mass, there is not much else that is under control. However, it is possible to study this phenomena, as I will show, by studying these theories that I mentioned compactified on R3 cross S1. So S1 is a circle where we take all the fermions to be periodic, so this is not a thermal circle. And it turns out that in this framework, in many theories, there is a weak coupling realization of confinement. And one can study non-perturbatively in a semi-classical weakly coupled way the physics of the vacuum. And interestingly enough, this is precisely what we did with Anber and Sulejmanpasic in 2015. We studied deconfinement on domain, we found deconfinement on domain walls without being cognizant of any anomalies or anything like that, because at that time we hadn't understood these generalized anomalies. We just did an honest semi-classical analysis. And what I will tell you about is how this can be done. And of course, I will extend it, adding some more insight from the knowledge of anomaly, which is more recent. Now, in order to proceed, I will further narrow the subject of my talk. I mentioned a bunch of theories in the beginning. All of them can be studied in this framework, but it is too much for one talk. So I will narrow the subject. I will narrow the subject to SUN, adjoint QCD, with a single massless adjoint bar fermion. So, sorry, this is also known as super Yang-Mills theory. And this theory falls in the class that I described. It has a Z2N chiral symmetry, discrete chiral symmetry, which is broken in the vacuum. And it has an unbroken one-form center symmetry. And these two symmetry has a mixed zero-form, one-form anomaly. I want to stress that the story I will tell does not require supersymmetry. there are these other classes of theory known as adjoint QCD, deformed Young-Mills, axion coupled to vector-like theories. However, explaining everything I will do, not using SUSY, will require another talk. So I will use supersymmetry to help streamline the presentation quite a bit. So this is my goal, and I will just declare the general features in the end. So the outline of my talk, well, the introduction is over. I will continue by a brief reminder of the symmetries and the Hooft anomalies of super Young-Mills. And I stress the word brief because I will have to assume familiarity with some of those things. There is no time to explain too many details. The bulk of my talk is really this part, where I will discuss the compactification, the scales, and the semi-classics, and will tell you how using effective field theory and symmetries, we can describe the domain walls, and we can see dynamically how quarks become deconfined on domain walls. So this will be the bulk of my talk. It entails those papers from 2015 and last year. And finally, I will conclude. I will remind you of what I told you about, and I have a wish list of things that I would like to understand. So this is my story. So let me continue with the reminder of symmetries and Hooft anomaly of super Young-Mills. So we have an SUN gauge theory with a massless adjoint Bal fermion. There it is. It's a two-component fermion. It's in the adjoint. Whoops. It has a center. It has a chiral symmetry. Classically, it has a U1 chiral symmetry, but under a U1 transformation, the measure of the path integral transforms like this, where Q topological is the topological charge. And so we see that unless alpha is an element of Z to N, this is not an invariance of the path integral measure. So quantum mechanically, the U1 symmetry is reduced to Z to N. In addition, there is a center symmetry which acts on topologically non-trivial Wilson loops of N-ality K by multiplying them by a Zn phase with the power K. And interestingly enough, these two symmetries have a mixed anomaly. And this is revealed by gauging the center symmetry. And the center symmetry can be gauged by using a two-form Zn gauge field. There is an entire formalism using continuum, using lattice, whatever. I can't really go describing that in great detail. But it's interesting that if one gauges the two-form, the one-form symmetry using a two-form gauge field, then one finds that this induces fractional topological charges. And I really like the lattice picture where the two-form Zn gauge field is just a plaquette-based gauge field. And what I have tried to show here is the set of plaquettes, the minimal set of plaquettes, which you can take to be non-vanishing. These are Zn-valued plaquettes fields. Of course, I cannot depict a four-dimensional lattice, but these are two intersecting thin center vortices, and they carry a fractional topological charge, which I have written like this here. And so if you gauge this if you introduce this two-form Zn gauge field background, this topological charge becomes fractional. And remember that under the Z to N symmetry, the measure transformed as e to the I 2 pi Q topological, but now Q topological in a background gauging the one-form symmetry is fractional. So this is not a symmetry anymore. Rather, there is a phase in the transformation of the path integral measure. This phase is the mixed center chiral Hooft anomaly. It is independent on the renormalization group scale. For example, if you think of the theory being defined of the torus, it doesn't depend on the scale of the torus. This phase has to be reproduced by the theory in any scale, at any scale. And this theory is matched, in this theory, this is matched in the infrared in the quote-unquote Goldstone mode, meaning that the Z to N symmetry is broken down to Z2. Of course, that fact has been known for a while. And there are domain walls. So in order to argue something about the physics of domain walls, some formalism is useful to make a connection to this world volume theory on the domain wall. So like any anomaly, this mixed chiral center anomaly that I represented here can be thought of as due to some anomaly-inflow, and there is a five-dimensional anomaly flow action which ends on the background gauge fields, which I have written here in a normalization, which is convenient for me. So this is an action over a five-dimensional manifold whose boundary is the four-dimensional manifold. A1 is the Z to N gauge field for the chiral symmetry, and B2 is the two-form gauge field for the center symmetry. And under a chiral transformation, this field shifts. This is a normal 0-4 transformation. The variation of this action localizes to the boundary. The parameter on the boundary you just take to be a Z2N phase. And then you find that this 5-dimensional action induces this change on the boundary. And this here just stands for, well, I took this to be a unit, 2-unit Hooft fluxes. So this is unity. So this change of this action is precisely I2 pi over n, which precisely gives this phase, okay? So this is one way of thinking about this mixed discrete chiral anomaly. But now what does this have to do with domain walls? So we can think about it like this. So if you have a theory that breaks the discrete symmetry, if you introduce twisted boundary conditions, for example, if you take the Ising model in a broken phase and you twist the boundary conditions, the way the system will react is by creating a domain wall to, you know, in the direction orthogonal to where you twisted the boundary conditions. So we can play the same game with this anomaly polynomial, anomaly action, and we can turn on a Wilson line, say a unit Wilson line for this Z2N gauge field in one of the directions of physical spacetime. Okay, so we know that the theory will react by creating a domain wall. And then this anomaly polynomial reduces to a 4-dimensional anomaly polynomial. And if the bulk is gapped, it's naturally to think that the variation under these remaining symmetries of this 4D anomaly polynomial will localize onto the world volume of the domain wall. And this is something that has 2 center symmetry gauge field. And it is known that 3-dimensional Chern-Simons theory has precisely this sort of anomaly polynomial for its Zn center symmetry. So this inflow action describes the anomaly, sorry, this is the anomaly inflow action, not the polynomial, the anomaly inflow action for a 3-dimensional Chern-Simons theory. So this means that to match this anomaly on the domain wall, it's natural to suppose that there is a 3-dimensional Chern-Simons theory. And by the arguments I said earlier, this implies that the Wilson loops in this theory obey perimeter law. So this is the
question.
Yes.
I don't understand the last comment. Why does this imply, if you assume that indeed you have SUN Chern-Simons theory there, I understand why there is no confinement, but that was an assumption.
Absolutely, yes. Yeah.
So
yeah.
What do you mean by hence no confinement?
Okay, if I
imagine you have
that
this anomaly and there's something else. Can you prove just from the anomaly that there's no confinement there?
I can't. No, I can't. I don't intend doing that. No, especially on. Yeah, I assume that there is a Chern-Simons theory. So that's my answer. So the rest of the talk, what I'll do is this. I will show you that we can reveal both the deconfinement on the domain walls and aspects of this domain wall Chern-Simons theory semiclassically. So we can dynamically see that it appears that this is a consistent assumption. Okay, so this is my goal. So in order to do that, as I said, I will consider the theory on R3 cross S1. So I briefly have to remind you of a few points. So the size of the S1 is L, and I will consider small sizes. And I have to tell you what that means. What that means is that N times L would be much smaller than the inverse strong coupling scale of the theory. So this is in sort of renormalization group invariant ways to formulate what I mean by small L. Oops. In different ways of phrasing is the 4-dimensional gauge coupling at the scale 1 over NL will be small, and N times L will be fixed. And this is this limit that corresponds to this limit. I want to emphasize that this is not a limit when the 3-dimensional gauge coupling is kept fixed as you take L to 0. So this is a different limit. So what happens in this framework that we study is the following. We have this theory, it has no scalar fields, but once you compactify on S1, there is a holonomy. So the component of the gauge field in the compact direction acts like a scalar because we've broken Lorentz invariance. So in terms of R3, it's a scalar. It can obtain an expectation value. And it turns out that in this theory, this holonomy fixes the SUN gauge theory to the maximal Cartan subgroup. And this Hicksing occurs at a scale of order 1 over NL. So the W boson mass goes like 1 over NL. So when you have this adjoint theory, which is Higgs to the Cartan, all the W bosons and their superpartners, they become heavy. At long distances, you have n-1 Cartan U1s. And this, in principle, these three-dimensional U1 couplings can run, but this is a theory with adjoints. So there is nothing charged under the Cartan once the breaking has occurred. So these couplings are frozen, they don't run, and they're weak if the scale of the W boson masses is much bigger than lambda, and this is this condition physically. And it turns out that if we use, in this weakly coupled theory, which would be very boring if there were just free U1, there are non-perturbative effects that can be studied in a systematic way, and one can study confinement, chiral symmetry breaking, etc. And this doesn't require supersymmetry. This is very generic to a large class of non-supersymmetric theories, but I will focus on super Young-Mills. And due to this fact that the size of the circle is not taken to be 0, this theory remembers many four-dimensional properties. It remembers anomalies and symmetries. The mass gap and the confinement at long distances is due to the proliferation of instanton-like objects, which are magnetic bions. So these are some very interesting objects, which are composites of some monopole instantons, and they occur in other theories as well. And this gives a locally four-dimensional, non-trivial generalization of the Polyakov confinement mechanism. Again, locally four-dimensional because the theory remembers the four-dimensional nature. There is more of these monopole instantons than just the three-dimensional ones. It is non-trivial because there are these magnetic bions that really are the causes for the confinement. Okay. Now, I'm using supersymmetry and effective field theory, and I cannot go into the details of all this semiclassical interpretation because it's just too much. What I will do is I will describe the infrared dynamics valid at length scale much bigger than NL using a three-dimensional effective field theory. It will be very instructive and very economical because I will skip many interesting details doing that. So as I said, this theory abelianizes at a scale 1 over NL. And so at long distances, there is only the Cartan gluons that participate in the dynamics. The arrow in what follows will denote a vector in the Cartan subalgebra of the group. F mu nu is the field strength tensor in the R3 directions. And so of course, I can dualize it to a dual photon. Okay? So for me, it will be very important to just remember that in terms of static dual photon configuration, the gradient of the dual photon is two-dimensional dual to the electric field. So that's important to remember. So a derivative of a gradient of the photon in the X is the electric field in Y and vice versa. Another interesting thing about these dual photons that they're compact variables. In the SUN theory, they live in the unit cell of the weight lattice. And this is a picture, so forget about the dots so far. This is just a reminder of the SU3 root and weight lattices. So alpha 1 and alpha 2 are the two simple roots of SU3, and W1 and W2 are the fundamental weights. So the dual photon lives in this torus here, made out by these fundamental weights. Okay, so it's a compact variable. So that will be important for what follows. The dots will come later. And so an important corollary from these relations is that if you have an electric charge, like an electric charge probe, introduced into this two-dimensional theory, instead of Gauss's law, which says that the electric field flux should measure the charge, here you have the monodromy of this dual photon. It gives you the charge inside. So it's just a consequence of that. And so it's important to remember that the monodromy gives 2 pi times the weight of the charge inside the loop. So lambda is the weights are the charges. So this should be familiar from the quark model, for example. Okay, so these W's, this one, and this one give the charges of quarks, this one, and this one give the antiquarks, etc. Okay. So this is one of the fields that will be very important for us. And in particular, this semi-classical interpretation is crucial for what follows. Another field that will be important is the following. It is the one that, so the electromagnetic field strength has components in R3. It also has components mixed in R3 and the compact direction, which I kept call for. And this phi is really a stand-in for the gauge field in the compact direction. Okay, so this is just a relabeling, it's dimensionless. And now we come to describing the symmetries a little bit. Oh, before I forget, yes. So the derivatives of this phi, that will play an important role too. the spatial derivatives of this field phi are two-dimensional duals of the magnetic field. So the x derivative of phi is like derivative of b in the y direction, etc. Okay, so that's important to remember. So this theory, as I discussed on R4, it has a one-form center symmetry. When you compactify the theory, it splits into a zero-form center and a one-form center. So I call the zero-form center, this will be my notation, ZN0C. It's not conventional, I don't know what it is, but that's what I will call it, is the center symmetry in the S1 direction. This center symmetry acts on Wilson loop compactified on S1. So this is a fundamental Wilson loop, and it acts like that. And I told you that this phi is a stand-in for the diagonal components of this A4, which is the component of the gauge field along the Cartan direction. And I have normalized, I've defined it so that zero expectation value of phi correspond to vanishing traces of the powers of the holonomy. So this phi equals 0 means that I am at the center symmetric point. So this is the trace of any power of the fundamental Wilson loop, which is not n, vanishes. So I will not derive that, but it is important to know how this field transforms under the zero-form center symmetry. The zero-form center symmetry acts on the holonomy, and because the holonomy depends on phi implicitly, I haven't written how, the zero-form center symmetry acts on phi as well. So I just assure you that it acts in some sort of embedding of the ZN symmetry into the symmetries of the weight lattice. And most precisely, there is a product of our reflections with respect to all simple.
Perhaps this is not the place to complain about it, but the phrase center symmetry is really a very confusing and inappropriate phrase. And in this particular example, it really comes to life because this symmetry is not the center associated with any center of anything.
Absolutely. It's the separate global symmetry of the theory. I am with you.
It is the symmetry of the system, and calling it center symmetry is really misleading.
Absolutely. This has stuck. I'm sorry, yes. But, you know, yes, I'm very precise at what it means. Yes.
It's okay to use misleading in terminology if it's already standard and too late to remove it. To introduce it in a new place is really funny.
Maybe I shouldn't. Okay, let's just call it ZN0C, just to distinguish it from the chiral symmetry, because there is another zero-form symmetry. So, but I may still slip my tongue, okay? It is not the center of the gauge group. It's a separate global symmetry of the theory. Absolutely, I am totally cognizant of that, okay? So anyway, it acts on this field phi by this precise way. I'll give you a picture, okay? But so this is one of the symmetries. It acts on the field phi. And now I will cheat a little bit. This is a supersymmetric theory, and phi and sigma are the lowest component of a chiral superfield. So if this symmetry acts on phi, it must also act on sigma, okay? This is the quick argument. So it is important for me that this one-form symmetry transformations along the compact direction to make Nati happy act on both the holonomy and the dual photon in identical way. There are non-SUSY arguments, of course, in the non-SUSY theories, but that's the quickest way that I can use SUSY, okay? So we have this symmetry, center symmetry along, sorry, the one-form symmetry along the compact circle, okay? So in addition, we have chiral symmetry. And the chiral symmetry was a Z2N symmetry on R4, but on these bosonic variables in the compactified theory, it only acts on the dual photon and it acts as a ZN symmetry. And it's a kind of an interesting story how it comes about. But roughly speaking, the chiral symmetry is intertwined with the would-be magnetic center symmetry of the dual photons. And that center symmetry is broken by monopole instantons. So this is a Hooft vertex for a monopole instanton, and under the Z2N, it transforms like this. These guys have zero modes, and so the sigma transformation looks like that, okay? So rho is the Val vector. I will give you a picture of what that is for SU3. So these are all things that come from the Lie algebraic structure, okay? So those are two of the symmetries. And so on R3, there are two zero-form symmetries, the zero-form chiral symmetry, which is now a ZN acting on the bosons. And there is this, what I call the zero-form center, if you want, is the one-form center symmetry along the S1. And finally, there is the one-form center symmetry or the one-form symmetry in the R3 direction, which I call ZN1C. Again, no standard notation. it is probed by Wilson loops, which are in the non-compact direction. So a Wilson loop looks like that. It's a trace in some representation of the path-ordered integral along R3. And once you go to our effective field theory, this just becomes a trace in the Cartan because the W bosons are heavy. And in the abelianized theory, I can use integration by parts to represent this integral over a contour C in terms of the field strength, or the B field, if you wish, just electrodynamics, and then I use the duality relation. So it is important that this trace becomes a sum over all the weights of the representation, so lambda are the weights, and for each weight, you have this object which you have to insert in the path integral if you want to compute the expectation value of the Wilson loop. To cut the long story short, insertion of this object, what it does is imposes a monodromy around the loop sigma, a monodromy of sigma of 2 pi lambda. So if you have this loop, this object tells you that the derivative, as you go around the loop anywhere, sigma should change by 2 pi lambda. Okay, so that's very important for us. So this is the kinematics that I'm interested about in. I'm not going to discuss the fermion fields at all because everything I'll do will just depend on the bosons. So this is the kinematic. What about the dynamics? So we said that we are working at small s1, and I introduced this complex field X, which is phi plus I sigma. That's my bosonic field. The super partners actually go for the right. So this is a weakly coupled theory. The kinetic term is simply the trace of the Cartan of the four-dimensional kinetic term. And this is simply the this thing where it's really the absolute value of X squared, the derivative of the absolute value of X squared. So this is simply the dual of that. The coefficient M, its precise value is not important for us. It's a perturbative scale. It's the scale, roughly speaking, the scale of the W boson masses. Okay, so there is a Keller metric associated with this theory. It is understood, but we will just take it to be diagonal. There are corrections to it, which actually have been calculated. And apart from studying the large N limit, they're not important. So we will ignore them here. Okay, so there is this perturbative scale. The dots here in the perturbation theory framework just denote higher derivative operators suppressed by the W boson mass, which will not be interesting for us at long distances. So this theory would be very boring if it was just this, because it's just a free field theory with some higher derivative term. However, there is a non-perturbative scale, which is of order 1 over L times e to the minus 4 pi squared over g squared. I will just call it little m. I will also call it the dual photon mass in what follows. Okay, and what's most interesting is that non-perturbative effects, really controlled by that scale, generate a potential for these fields. And this potential I have chosen to normalize like this. This potential is due to a superpotential. Okay, so in terms of supersymmetric terminology, this just becomes a West-Zumino model or a Landau-Ginzburg model with a particular non-perturbative superpotential, which I have written here in a way which is convenient for me. You may have seen it before in a different manner. So written in terms of n-1 variables capital X, and then another variable which is the inverse of the products of those. But this top parametrization is very convenient for me because I really cherish the semi-classical interpretation of these little x vector fields. So that's very important for me. So talking about this potential using a superpotential language is a way for me to avoid discussing the details of the semi-classics and magnetic bands and everything like that, which I would have to do in a non-supersymmetric theory. So probably the first place this was written in this context was a paper of Seiberg and Witten about three-dimensional dynamics back in 1996, I believe they wrote this potential first. So now we can study this model and ask about confinement and the properties of strings and domain walls in this model. So it is a simple exercise to show that this theory, this supersymmetric theory, has n vacua, and all these vacua are gapped. So the scale of the mass gap is set by little m, the non-perturbative scale. It's pretty clear from here that that should be the case. So these vacua all have zero expectation value of the holonomy. So the what I call the zero form center is unbroken. And these vacua have different expectation values for the dual photon fields, which are some sort of integers times this Weil vector over n. So of course, I'm not deriving this, but I'll give you a picture for SU3, which will be very useful in what follows. So again, this is my fundamental region of the dual photon field, the fundamental cell of the weight lattice for SU3. And the dark dots are really the minimum of the potential. So remember, the dual photon is a periodic field. So this is not a different vacuum than this one, but 1, 2, and 3 are different vacua. And these 3 vacua correspond to the spontaneously broken chiral symmetry. The Weyl vector is the sum of the 2 fundamental weights. So is this, and the Weyl vector over 3 is this and this. So a chiral symmetry takes you from here to here, from here, and back to 1. And the zero form, what I call the zero form center, the one form symmetry along the compact direction acts on a dual photon by 120-degree rotation. This is this embedding of the Z3 symmetry. So the way to see that it's unbroken, for example, in vacuum 2, 120-degree rotation take this point to this point, but then it's a shift by W1, which is an identification. So it's obvious that it's an unbroken symmetry. That will be important in what follows. So this is the story about the vacua. They're N vacua. The Z to N symmetry is broken down to Z2. So this is just like in 4 dimensions. This vacua can be conveniently depicted by showing the expectation values of the superpotential, the values of the superpotential in the vacua. Those lie on a circle of radius n. It's not important for us. So the dots are the vacuum values of the superpotential. So they're N vacua, and there can be domain walls between them. And domain walls can be denoted by straight lines. And as a matter of fact, for BP, never mind. Okay, so this is a one wall, so it goes between neighboring vacua. This is another wall which goes 4 vacua across. So the terminology is a K wall interpolates between vacua K units apart. And as a matter of fact, the tension of BPS walls is related to the length of these lines. Okay, so what is important for us is this. What's important is that the value of the dual photon is different in 2 vacua. So across a wall, for example, across a one wall from here to here, the dual photon changes by 2 pi over n rho. So in order for it to change, it means that it has the derivative. So across the wall, there is a derivative of the dual photon because it has to go from one value to another value. And by the duality relation, this means that there is an electric field in the direction of the wall. So this is familiar. These domain walls, or rather domain lines, I will call them walls, but they're lines. They carry electric flux along their world volume. So, oops. Okay, very good. So this is the picture. So this is one vacuum, this is another vacuum, and the gradient of the dual photon is this way, and there is a chromoelectric flux this way. Okay, so this is an illustration, and this is familiar from the physics of the Polyakov model, for example. What's interesting here, though, that as opposed to the Polyakov model, the flux that these domain walls carries do not correspond to the flux of any quark. In some sense, it's too small. And ultimately, this fact is due to the composite nature of magnetic bias, if you think of the Polyakov model in some sort of as a Euclidean gas of some objects. So what this means is that the domain walls, these lines where the flux can penetrate the vacuum, are not the confining strings in this model, unlike, for example, in the Polyakov model or deformed Young-Mills. Okay, so again, in those models, these are not domain walls, they're just domain walls type configurations. They're not stable objects. Here, these are stable objects. So the question that arises then is the following. We want to understand what are the electric fluxes of the lowest tension BPS walls. So first of all, the reason this is important because we want to understand confining strings, right? So the point about this picture is that the electric field in this confining vacuum cannot spread out like it would if there was no confinement. It can only go in these linear filaments that spread through space. So we want to understand what kind of fluxes these linear filaments of lowest tension can carry, okay? So we want to understand the fluxes of the lowest tension BPS walls. So these dual photons are compact scalars, and they have these extra monodromies that can occur across walls. So we want to understand this. And for K-equal 1 walls, we understood that a long time ago with Anber and Sulejmanpasic. And the reason for this project last year is that I was very confused about K bigger than 1 walls. And so we wanted to understand that. But let me first tell you about K-equal 1 walls. And there is 2 reasons for that. The basic physics can be understood using, confinement can be understood using K-equal 1 walls. And also, the SU3 theory only has K equal 1 walls because a vacuum 2 units apart is the same, is also 1 unit apart. And for SU3, I can actually plot things. So here's again my space of the dual photon plane. This is my fundamental region, and these are my 3 ground states, 1, 2, and 3. So a domain wall configuration between 1 and 2 will have the dual photon field change somehow in this direction. So it will change from here to here. So this just denotes the amount of change of dual photon between the vacua 1 and 2. So that's fine. Now, this theory has an unbroken Z3 symmetry, which is the one-form symmetry along the compact direction. So an unbroken symmetry transformation of the domain wall should be another domain wall. So it's this domain wall, right? So it's 120-degree rotation. And there should be yet another domain wall, which is the one that goes this way. And so there are actually 2 images, or a Z3 multiplet of domain walls between the vacua 1 and 2. You can bring them in the fundamental domains by shifting, okay? So it turns out that this generalizes for SUN, and the BPS K equal 1 walls all carry fluxes which are 2 pi n over rho minus subtraction of all the fundamental weights, including 0. So they're n walls, and they're related by the Zn center symmetry, or by the center symmetry along the compact direction, okay, which acts now as a 0-form symmetry. So these walls are related, and these are the fluxes they carry. So now if we want to, so as I said, the fluxes that these walls carry are not the fluxes of quarks. But what you see from this picture is that if you have 2 walls, one from vacuum 1 to vacuum 2, and one from vacuum 2 back to the image of vacuum 1, then the sum of these 2 fluxes, the vector sum of these 2 fluxes is W1. And W1, of course, is the highest weight of the fundamental representation. So it's the flux of a single quark. And suppose we insert a Wilson loop in the vacuum. So this is a rectangular Wilson loop inserted in R3. So there is a quark and an antiquark. And as I said, their flux cannot spread. So their flux has to do something. So what happens in the Polyakov model is that there are these objects which carry precisely the flux of the quark. And so they carry all the flux. And so this would be a picture in the Polyakov model. There will be a sheet of flux, which is the confining string stretching between these quarks. But in our case, there is no object that carries the flux of the quark. There is an object that carries, in some sense, half the flux of the quark, you know, this one. So there has to be another sheet, sort of presumably going down, which carries the rest of the flux. So this is what we suggested back in 2015. And indeed, this is what happens. We can actually, even then, we studied this numerically for SU2. We can insert a Wilson loop in the vacuum, and we can impose the monodromies around the Wilson loop, and we can have the configuration relax to the minimum energy configuration. And this can be done, and this was done for SU3 and for many gauge groups up to SU8 or SU9 this summer. So this, what is plotted here, is a cross-section of this configuration. So there is a quark and an antiquark of weight W1 and minus W1. And what is plotted is the energy density compared to the vacuum. So outside here, so this Wilson loop is going outside of the page. So it's a 2-dimensional, it's a Wilson loop in R3, but it's translationally invariant in, let's say, the time direction, which is outside the page. So this is this double sheet configuration. And we'll see that part of the flux goes along this domain wall. So this is this domain wall. And part of the flux goes on the bottom, on the other domain wall. And there is the other vacuum inside. And so these domain walls typically repel because these are not identical domain wall. But there is also some energy cost to having them far away because the energy is increased. So the relaxing configuration has this sort of shape. Okay. And it turns out that for all highest weight, for quarks of highest weights of all representation, you can arrange such a configuration. So So this is the picture of the confining string. So it's different than the Polakov model. Ultimately, the reason for this thing is the nature of the magnetic bias. So the gas, the charges of the magnetic bias are roughly twice as large. And so the flux that the domain walls carry is twice as small, roughly speaking. So what does this have to do with deconfinement? Well, it's a very simple exercise to do the following thing. So we can just imagine opening up this picture. So you cut this string open and you take this to go to the left and another part to go to the right, and you obtain this picture. So you have a quark and an anti-quark. Their flux is absorbed by these domain lines. And there is vacuum 1 on the top. Actually, I cut the bottom one here. Vacuum 1 on the top and vacuum 2 on the bottom. And the reason there is deconfinement on the one wall is that the BPS tension, the tensions of these walls are the same. So in this case, these are BPS walls, but you can also argue that it's based on the center symmetry because they're symmetry related. And because the tensions are the same, there is no energy cost to separating. And in fact, you can study that numerically. So these are, by the way, honest to God numerical simulations. I didn't just draw them. Okay? So you can study numerically the energy of this configuration. So I believe this is for an SU2 theory, this is for an SU3 theory as a function of the separation. And I haven't properly displayed the units, but what happens is that at distances between the quark and an anti-quark bigger than about 2 inverse dual photon masses, you find that the energy is independent of the separation. And of course, at shorter distances, you should be seeing the Coulomb law, which is some law in 2 dimensions. Okay, so this is the physics of deconfinement. And on K equal 1 walls, it works like this for all representations. And so what I was very confused about earlier, oh, sorry, let me continue with the K equal 1 walls. So I showed you, I promised you earlier that semi-classically, we will reveal 2 things. One was the deconfinement on domain walls, and the other was some aspects of the Chern-Simons theory. So I told you about, yes.
Yeah. Just make sure. So the previous slide is the double confining string. The double here, is that the double related to the number of color, say NC minus 1? Or this case,
it's double just because there are 2 strings. You see, the string has this structure. So this is just a name, okay? Probably unfortunate. But, you know, normally when you think of a confining string, you just think as a string that, you know, it's a one-dimensional object with, you know, by double, it just means that this confining string is composed of 2 domain walls. This is all I want to say. Okay.
Why particularly 2 domain walls, not more or less?
Well, because of the combinatorics of fluxes. So the correct statement is the following. If you take quarks, which are in the highest weight representation of any anality, there exist BPS 1 walls, such that you can arrange such a configuration. So to argue that, you just need to know the fluxes of the walls. Okay. Remember that the flux of the quark has to be split between this wall and this wall. And there always exists BPS 1 walls such that the sum of the fluxes of 2 BPS walls is precisely the highest weight of any representation. So the highest weight of any analytic representation is confined by BPS 1 walls. And we can argue that this is the lowest tension configuration because the BPS 1 walls are the lowest tension walls. There is some formula for the tension, and the tension of K walls grows with K, but 1 walls are the smallest tension. And of course, you have to argue that the tension of this string is really dominated by the tension of the BPS wall, but that's, if this configuration persists as you increase the radius, that's gonna be the case. So, so indeed, it's a double string for the highest weights of any representation. Does this answer it, or?
In your paper, you draw this figure for SU3, NC equals 3, but you said this configuration will be.
This is like true for any. This is true for any NC. Yes. So I told you that the BPS K wall, BPS 1 walls carry these fluxes, and yes, yeah. So this sort of configuration is true for any representation quarks. Okay. So it follows from the knowledge of the fluxes of the BPS walls. So you can always arrange a two-string configuration out of BPS K-walls to confine any highest weight representation.
So let me see if I understand what computation
Yes.
you actually do when you say
Yes.
numerics and all
Actually,
that.
oh, okay, go ahead. Yeah.
So you take the microscopic four-dimensional Lagrangian, you put it on this space, and you analyze it at weak coupling.
I use the Lagrangian that I just, this one.
And
So
in what limit is this Lagrangian accurate?
This Lagrangian is accurate in the limit when lambda and L is much smaller than 1.
Right, so this Lagrangian is nothing but the UV Lagrangian restricted to some light modes.
Absolutely, yes, the W bosons are integrated out, yes.
Excellent, so you're really analyzing essentially semiclassical, the semiclassical four-dimensional gauge theory.
Absolutely, yes.
Right, but then when you cross the wall, the fields are very far from the ground state.
The thing is that they're not, you see? No, they're not. That's the thing, yes. And actually, that was another reason we studied the numerics. This is kind of on my last slide. I didn't show you any profile, but this is no, they're not. That's the funny thing. They stay within the effective theory. So this is how the dual photon changes, and this is how the holonomy field changes. So this is the field phi. I don't have the units here, but you see the holonomy field, indeed, if you go far away from the center symmetric point, you can hit a point where W bosons become massless, and then your effective theory breaks down, right? So if you hit the wall of the Weil chamber, you're dead. That never happens. This stays really close, okay? So you stay within the effective theory. You never hit the walls of the Weil chamber, right? Remember, this is the field phi lives in some. Do you see what I'm saying? You're not happy with that, but okay.
The reason I find it surprising is that in the same problem in R4, the fields on the wall are very, very non-perturbative.
Yeah, that's not the case here. And the reason is that it's small l. You see, the coupling in this theory never becomes large. The theory is weakly coupled at all scales. That's the thing. You see, provided L is small. Near the center symmetric point. Of course, if you go far from the center symmetric point, yes, but you don't go far. So it's a kind of a self-consistent thing. You see, it's
is the bulk gapped or not?
Absolutely, yes. The bulk is gapped. Yes, yes, yeah. So can I, let me do this. It's even, I can write something. Why do I have this open? I assume you don't see my screen now, right? So I will do this. You see, it's even simpler in the SU, whoops, yeah. In the SU2 theory, so the effective Lagrangian is very simple, actually. It's d phi squared, because there is one holonomy field, and d sigma squared. And the potential is cosh of 2 phi minus cosine of 2 sigma. And so this is the non-perturbative potential. So this has a factor of m squared. So this is my effective Lagrangian. So in this theory, a confining configuration is just sigma goes to sigma plus pi. And phi is constant, actually. Phi never changes. So phi stays at the center symmetric point. So in this effective Lagrangian, there is a confining configuration that it doesn't take you away from the center symmetric point at all. And it's consistent within the effective theory. There is absolutely I have no doubts about that.
So I still find it surprising that confinement, which is normally attributed to strong coupling phenomena, or at least non-perturbative.
Well, this is non-perturbative. The second thing is this is non-perturbative superpotential.
Yeah, but it is an instanton.
Yeah, absolutely. But you see, it's instanton, but it's in the semiclassical regime. So SU2, oops, SU2 is broken down to a U1 at a high scale. and the scale is 1 over L, and L is fixed and small. And this phi is the deviation from the center symmetric point, and you actually never deviate. For other groups, you do, but for here, absolutely not. Look, the confinement in the Polyakov model is also semiclassical. It's not strong coupling, right? It's just the proliferation of monopole instantons. The effect is tiny. The effect is tiny. This is a tiny scale. M is a tiny scale. So M squared is like e to the minus 8 pi squared over g squared times 1 over L squared. So it's a tiny effect, but still, it's essentially it's like in the Polyakov model, except for some subtleties with the charges. You're not happy.
No, I'm delighted. You don't. My camera is turned off. You don't see my big.
Oh no, no! I think this is fantastic. Okay, this doesn't happen very often. You know, this is why I like Unsal's work so much. You know, I mean, I know it's not the real world, but it's what it is. So I'll go back to my slides now. Where is it here? Yeah. Yeah, so, and again, for SU3 on SUN theories, this is what happens similar. I mean, this field phi actually changes a bit. It departs from the center symmetric point, but it doesn't go anywhere near the parts where semiclassics breaks down. It's true, okay? Okay, whew. Any other questions? I mean, this is fun. We're kind of running out of time, but we don't have that much more, you know? So I promised you confinement and deconfinement. Here they are. It's within the semiclassical picture. It is small l, okay? It is small l. Large L, yeah.
I mean, the seminar is actually 90 minutes, so you have a lot of time.
Okay, can you see my screen actually?
Yes.
Do you see the screen? Okay, yeah. Okay, yes, fine, yes, yeah.
Full screen is fine.
Yeah.
Right now,
okay.
yeah.
So again, to answer Juven's question, it's the double confining string is just the fact that the confining string for quarks in the highest weight representation of any anality, I believe, it's not proven, but I believe, and there is a summer project going on right now actually, which will shed some more light on this, that the confining string for quarks in any highest weight representation, so for the weight being W1, W2 down to Wn minus 1, I believe that the lowest tension string is always composed of two domain walls with one vacuum inside and a neighboring vacuum inside. So these are K1 walls, the lowest tension. Again, it's not proven, but it's true. And this is consistent within the semi-classical picture. You know, all we have done is find the minimum action configuration or minimum energy configuration, because everything is static, of the sigma field and the flight field subject to these monodromies. We can study how it changes as you increase the distance between the quarks, but it's very honest thing, okay? And it gives the confinement of quarks. Okay, this picture is inherently contains that phenomenon. All right, so I promised you deconfinement on domain walls. I hope I convinced you that it's true. It's within this effective field theory. It does not break down on the domain wall either. What about domain wall Chern-Simons? Okay, so so here's my argument. So they're n-degenerate one walls, okay, as I argued. So they have these fluxes. They are different walls between neighboring vacua. Their fluxes are 2 pi n over rho, as required by the fact that you connect neighboring vacua. And then you add to those fluxes any fundamental weight, including no fundamental weight, okay? And there are n of them. They're related by the unbroken one-form symmetry along S1, okay? And so now, I think that talking about the world volume TQFT, I think it's a matter of interpretation. I can say this. I can interpret each of these one walls as a state in some world volume theory that has some finite dimensional Hilbert space. So this world volume TQFT should be oblivious to precisely what the fluxes are and the structure of the wall or anything like that. So we just want a TQFT that has n states. And well, there is a natural candidate. It's a two-dimensional theory because the world volume of these walls is a line plus time. And the most natural thing is the two-dimensional Zn TQFT. And this is very consistent with anomalies. because you write this ZNTQFT. It has n ground state, of course. So it has a zero form symmetry where this phi shifts by 2 pi over n. So by the way, phi is a compact scalar, A is a compact U1 field. And there is a one form symmetry where A shifts by 1 over n times a closed form, which is integer period. So it has these two symmetries. And if you gauge them, I haven't done that here, but it reproduces the mixed anomaly with this, with the dimensional reduction of this 4-dimensional polynomial that I wrote. So it kind of makes sense. And it's also the dimensional reduction of 3-dimensional U1 transimers. I think that's true. Correct me if I'm wrong. But so this is how I interpret a world volume TQFT. We have a dynamical picture where we have all these walls. We interpret them as different states, and then we write the TQFT. So that's my that's the story about this. Okay. And so next we come to K-walls, and this is what was very confusing for me. What were these K-walls? And it's very interesting result. Okay, so basically my collaborators initially numerically found what are the fluxes of BPS walls. Basically, because this dual photon space is very large, you can add arbitrary numbers of fundamental weight vectors, but most of these walls are not going to be BPS. But you can keep adding fundamental weights and ask at what point the tension of the walls increases. And that was done initially numerically, and then we found a symmetry argument for that. And so what we found is that the K walls, the electric fluxes, they fall into groups. So in every case, you have to have a flux which is 2 pi K over n rho, because you have to go between vacua K units apart. The question is, what are these periods that you add, the 2 pi W fluxes that you add? And it turns out that there are two groups. In one group, you have this flux 2 pi K over n rho, which is the flux between the vacua K units apart. And in one case, you add K fundamental weights, which are not all the same. And in the other case, you add K minus 1 fundamental weights, which are not the same. So these are all different walls. From the top, there are n minus 1 choose K, because these are fundamental weights. There are n minus 1 options, and you have to choose K of them. And from the bottom, there are n minus 1 fundamental weights, but you have to choose K minus 1. And there is a remarkable identity, just the sum of those two is n choose K. And this should ring a bell, because the number of BPS K walls in Landau-Ginzburg model has been known for a very long time. There is some very sophisticated machinery by Chicotti and Baffa and others. And this n choose K has been known for a while. So this is an old story. We're very happy. But the new story is that we understand what electric fluxes they carry, right? So they carry, we know that the BPS walls, the lowest tension walls, which we know the tension of these walls. We can, it follows from the BPS formula, and we can numerically verify this. We know what fluxes this wall carry. And so we know what quarks they can confine. Okay, and we have arguments in the paper that these are all BPS walls, using some arguments from these papers. So by the way, for K equal 1, this reduces to the previous case, because if K is 1, this is just one wall, and there are just n minus 1 out of this. So everything works like that. So we know what these walls, the fluxes are. We also know that all these walls are within the validity of the effective field theory. There is nothing massless or anything like that staying there. So we can use the fact that we know the fluxes of these walls to construct configurations where a quark of a given weight, for example, the highest weight of the Q index antisymmetric representation, can hang between two K walls of equal tension. And the condition is that this wall carry fluxes so that the flux of the quark is split to the left and to the right. Right? So here I have vacuum 0 on the top and vacuum K on the bottom. In vacuum 0, the dual photon has this value, 2 pi K over n rho, in vacuum K. In vacuum 0, the left domain wall I take to be the vacuum 0 plus the addition of these fluxes. And on the right, I take the vacuum 0 plus the addition of Q. And those were precisely in the list I have. And so for a weight Q, the fluxes of this wall precisely absorb the weight of the quark. And if I put an anti-quark, they can be separated without any energy cost, because these walls have the same tension. That's the condition, that they're BPS walls and they carry the same tension. So we get the same picture as here. but for walls separating vacua and K units apart. So, essentially what this means that for any representation quarks, we get a perimeter law. So this is the dynamical explanation of deconfinement for any K wall. So I think I'm actually mostly done, and now I can go on to the conclusions and my wish list. So first, what did I tell you about? So there is this regime of Yang-Mills theory where I can do calculations. It's at small L on R3 cross S1. The theory is weakly coupled, including the world volume of domain walls. You never go through strong coupling. So the anomalies, vacuum structure, confinement, and deconfinement are intertwined in some intricate ways. We studied this example and how this anomaly is matched, leading to deconfinement of quarks. I find the picture very appealing and comforting. It's a detailed understanding of this double string confinement on R3 cross S1. And I should just say that it applies to various non-SUSY models, which are also formulated on R3 cross S1 with appropriate deformations or some massive adjoint fields added something, okay? But it's very interesting that whenever there is some anomaly, like between CP and center symmetry and one-form symmetry, or something is... Somebody is talking and I don't hear anything. Okay, are you guys hearing somebody talking okay, do you hear me?
Somebody's talking.
There was some background. There was some background. I think it's fine now, okay? So whenever there is an anomaly, it turns out an anomaly that you would think would lead to the confinement of strings is always this double string configuration occurs. So this picture is very generic. This is what I was. So this picture of confinement is very generic for all models which have a mixed anomaly between some discrete chiral symmetry and center symmetry. And the deconfinement of walls is explained in this picture. And in all these examples, these walls occur at small l within the semi-classical validity of the theory. So this is essentially my summary. There is a paper I wrote with Anber recently on axion domain walls. So there is some different scales that contribute. I don't have time to talk about that. So let me go to my wish list. So it has been argued that symmetry and anomaly is often not enough to fix the domain world volume TQFT. And in the case at hand, we only understand the TQFT on the K equal 1 walls as I described. For K bigger than 1 domain walls, we understand what the walls are and what their fluxes are, but I don't know how to write a TQFT. I just don't know that much about TQFT, and it may be related to the combinatorics of fluxes and the way the zero form center symmetry acts on them. These various fluxes of 1 walls, these various fluxes of K walls, the way they transform under the Zn one form symmetry along the compact direction is quite intricate. And so I haven't understood that. And many of these wish lists, maybe they're trivial for some people. I just throw them out because I haven't, I've had other duties and other interests that have gotten in the way, but maybe they're trivial for some of you. I don't know. But for K bigger than 1 walls, this is open. Okay, I don't know what the TQFT is, but we understand the walls and the fluxes. It's interesting that for super Yang-Mills, this same analysis can be repeated for all gauge groups, for all simple gauge group, because it turns out they're all tractable at small l. And some of them have center symmetry, some of them don't have center symmetry, so some will have anomalies, some won't have anomaly. So the same story can be repeated and the same questions can be asked within the calculable regime. There is another question related to some papers that I mentioned early on. So if you study these solutions, what you find is that these domain walls also carry magnetic fields. Mind you, they don't carry magnetic flux, but essentially this is because there is a nonlinear coupling between what you could call E and B, or sigma and phi, due to this superpotential. And this is the picture I was showing Nati earlier. So there is this for SU3, this is a K equal 1 wall. There are 2 sigma fields, that's what they do. They go from one vacuum to another, is what you expect. But the phi field, which is the behavior of the holonomy, so these are the 2 eigenvalues of the holonomy, they just behave like that. And remember that the derivative of phi was the magnetic field. So what this means is that the wall sort of has a magnetic field going in one direction in half of the wall, and then it goes in the other direction in the other half of the wall. So, for most of the walls we discussed, there are these magnetic walls, magnetic fields on the world bottom. So, however, numerically and then analytically, what we found is that there is some very special situations where magnetless solutions appear. So this happens for k equal n over 2 walls in even SUN. So it turns out, so that's the case for SU2, of course, when for k equal 1 walls that fits in. But for those walls, magnetic fields don't appear. And we showed that these walls without magnetic fields exist only for k equals n over 2 walls. And moreover, by studying the BPS equations and looking for the properties of that solution, it's a kind of a painful combinatorial analysis, but out of the n choose 2 BPS k equal n over 2 walls, we found that there are only 2 walls with no magnetic fields if n is not divisible by 4, and only 6 walls with no magnetic fields if n is divisible by 4. Moreover, all of these walls with no magnetic fields can be constructed by embedding the analytic solution for SU2 walls. The only wall which is known analytically is the one for SU2. So this is quite interesting. And the reason n over 2 walls may be interesting and there be more structure is that in general, k and n minus k wall are related by some rotation in space-time and a reversal of the world volume flux. And if k is n over 2, this is some transformation that acts on the wall. And these recent papers discussed cases where that is the case. So what I'm thinking is that maybe these facts, which are very painfully obtained before, may have a quicker symmetry explanation. And I don't know the answer, okay? But there is some special properties of walls which can add vacua n over 2 units apart. So this is my third wish list item. And the fourth item, of course, is the most interesting. And this is thinking about an excursion to R4. So remember, we have this theory that we are considering at small l. And we found that when we consider the theory at small l and we ignore the dependence on the S1 coordinate, integrating out all the heavy W bosons, etc., self-consistently, we found that quarks can hang in on a wall, and the picture looks like that. The wall is a line in R2 in this theory, and that's more or less the picture we found. Okay, so the flux is absorbed, the tensions are the same, and the quarks move left and right. Okay, now what's interesting is that there are other arguments using Chern-Simons theory and also other arguments, which imply that deconfined quarks on the walls are actually anyons. So they actually break. And clearly in Chern-Simons theory, that's automatic. Now, in our two-dimensional world wall setup, this is not visible because the quarks have to pass through each other. So clearly that we cannot do. But in reality, what we are actually studying is the following. So this is a difficult picture to do, but these walls, we should really think of them as wrapped on the S1. And so, but our quarks are localized in R3. So our picture is really something like that, where the quarks are on the walls on a given position of S1. And the flux is somehow actually spreading on this wrapped domain wall. And so our S1 is small but infinite. But as I said, the theory is weakly coupled at all scales. And going across the domain wall doesn't change that. And so I think that maybe in this small L setup, when in the weak coupling regime of the theory, without going outside of its validity, it is possible to see that there will be some phase induced when these quarks go around each other. I don't know. I think there is hope, but then the main thing that one has to accomplish is to describe what I said without using the 3D duality and the effective field theory. But again, my argument is that the theory is weakly coupled at all scales, and I think this may be possible and there is hope. It's an interesting thing to think about. So I'm done, and what I'm going to do is just leave you with some pictures of the color fields to contemplate and take any questions if there are.
Thanks for the lecture. Can I ask maybe 1 or 2 questions?
No, of course.
Well, maybe 1 comment also. So one question is that there is some literature from the 80s with a very intriguing idea about what more monopoles are supposed to be, like these elusive monopoles that you mentioned.
Yes, yes, yes.
So the idea is that if you take n fundamental strings, so they sort of cancel the string charge. And at the intersection of n fundamental strings, you get a monopole. So that's how it's realized on the lattice, that monopoles are like at the intersections of n fundamental strings.
Uh-huh.
Is there any way to connect? I mean, so you have some kind of monopoles after the circle compactification. You have what?
Yes.
So is there any way to see this kind of sort of qualitative picture, or?
Off the top of my head, I cannot say. No.
I see.
I don't know, Zahar. No, I don't know.
Okay. Another small comment is about the topological filter that you
Yeah,
get after
please.
compactifying on S1. I think isn't like G mod G the obvious conjecture?
I have no idea what that is.
Oh. I mean, for G equals U1, that exactly reproduces the BF type theory that you wrote. This 5
Yes, uh-huh.
A1. I mean, G mod G at level at the appropriate level should be the obvious conjecture. But okay.
Well, I'm happy to reveal my ignorance, Zahar. Yeah.
And maybe a very, very last point. I think at the beginning there was a question of whether this anomaly that you mentioned, B wedge B, implies deconfinement.
Yes.
And I think the answer is probably positive.
Okay.
I mean, if you have this B wedge B anomaly, then two Wilson lines must braid, because the coefficient of the anomaly is just the braiding of two fundamental Wilson lines. And if there is a
Yes, yes.
Sorry, not braid, link. I mean,
link, yes. Uh-huh.
the same. So there must be a non-trivial phase in the linking.
Mm-hmm.
And that's inconsistent with an area law, because if you have an area law, then you cannot have such a non-trivial linking, because if you just multiply the area by 2, there couldn't be some constant.
Mm-hmm.
I think that remains. That's an argument, I think, from the 70s by Hooft.
Mm-hmm. Mm-hmm.
So, okay, well, thanks anyway very much. It was educational.
Okay. Any other question I'm happy to entertain?
I'm still confused about what we can extract from this computation. I guess it's small l that you do, where everything is weakly coupled. How much of the information from there is reliable in the four-dimensional theory when L is large?
Oh,
so,
very
for
good.
example, there are some examples where in 4 dimensions, the theory is gapped in the bulk, but there's a discrete gauge theory there. And this discrete gauge theory is very non-perturbative. I would be curious if this kind of argument leads to that gauge theory. And more generally, as you make the L bigger, there could be a phase transition. And then the argument based on small l will need to be strengthened in order to pull these arguments through a possible phase transition to large L.
Absolutely. I think in general non-supersymmetric theory, I think probably there are phase transitions.
Even in supersymmetric theories, the theory on the wall can jump.
Oh, absolutely. You know, yes. I don't think this double string picture will persist. Absolutely. Yes. Yes. Yeah. Yeah. Probably true. Probably true. Yes. Yeah. So in general, I don't know the answer to this question. Yeah. Yeah. But
let me sharpen that. There are many other cases where it's quite confusing. So for example, imagine you study a theory with a non-trivial, with trivial center, for example, E8 gauge theory.
okay.
Or I don't know, one of the other exceptional groups that has no center. Then there's no argument based on anomalies. And yet I believe that the weak coupling analysis would suggest that there is indeed a TQFT there in some limit. Now, it's not clear to me that this TQFT will survive because it's not protected by any anomaly.
Yeah.
And the notion of confinement or deconfinement will not arise because there's no...
Yes, exactly. Yes, yes. Yeah. Yeah. Yeah, no, it's probably true. Yeah, Nati, I have nothing to say about that. Yeah.
I posted a question in the chat. Maybe I can ask it now. Is
So-
there a regime where you have a network of domain walls?
Oh, yeah.
And if so, what's the effective theory describing the dynamics of the network?
Oh, I have no idea. Okay. But yeah, absolutely. So for example, the simplest network would be this. So just imagine this sort of Mercedes. Oh, can you see my screen?
Yeah.
Yeah. Yeah. So the simplest network in SU3 would be a Mercedes star configuration. Now forget about the lattice. This is just space. And you can have this extend to infinity, this extend to infinity, and this extend to infinity. And you can have the three vacua here. So this is the simplest sort of thing.
A trijunction.
Yeah, a trijunction is the simplest one. And you can use BPS rules, and this is actually BPS junction. And you can have other things. I am not cognizant of that. Okay, I know Gayoto wrote a paper about this. He suggested that there is some Kazama-Suzuki models, but this is in the case where the junction is two-dimensional. Here, the junction is one-dimensional. The junction is just quantum mechanics.
And just to be clear,
I put in the chat a recent paper which addresses some of these issues.
Actually,
fantastic.
I don't see the chat. Very interesting. Oh, there is a chat. I see. Okay, I see. Okay, yes. I see. Okay, very nice.
Yeah.
I see. No, I don't know much about that.
Yeah, and just to clarify, the domain walls, you were drawing them as straight lines,
Yeah.
but need they be, in a dynamic sense, if it's a network, need they be straight lines, or can they?
Oh no, they can fluctuate, of course. Yes, but they're semi-classical walls, so it's costly. Of course, oh, and of course they have Goldstone bosons on their world volume, so yes, there can be some small fluctuations. I was just drawing the ground state. Yes, no fluctuations, but absolutely, yeah. Yeah.
More questions from the audience?
Isn't there a proposal about E7 gauge theory and what are the walls, what's the dynamics, and how rigorous is that?
I don't know. Yeah. I don't know.
Sorry, can you hear me?
Yeah.
Just a big question, I don't know. So I was wondering if, what if one consider fermions in other representations also within the, along with the joint QCD? What are the analysis? Were there,
Okay.
like, for example, fundamental, anti-fundamental? Yeah.
Yeah, this, so in general, this nice semi-classical picture is lost. And it's very difficult to give a general answer. So the adjoint case is very special, both in the supersymmetric and the non-supersymmetric case, that abelianization occurs dynamically. Very often there is an unbroken non-abelian gauge group, or even if there is an abelianization, there is charged matter under the three-dimensional U1s and the theory becomes strong. So in order to avoid that, one has to start turning on some flavor type Wilson lines and play games like this. So I don't think there is a universal answer to that question. So that's a very brief answer, but from what I know, it's not an easy thing to do.
I see. Thanks.
I should first say to Eric that Blago Dariati.
Oh, thank you. Thank you, Julian. Thank you so much. Yes. Thank you, everybody, for the questions. Yes. Okay. So I accept questions by email too, if I can help. Okay,
Just
so
wait
thank you
for
very much.
that.
Thank you very much. Thank you.
If there are more questions, благодаря много.
No,
Derek.
thank you. Thank you, Jovan. Благодаря, Jovan, for the invitation. Thank you. It's a good start of my diving trip, if you see my background. Thank you.
Thank you. No question.
Are we done? Yeah.
Yeah, if not, then that's a follow to. Thank you very much.
Thank you. Thank you, everybody.